All right. Hello, everyone, and welcome to today's webinar, Harvesting Carbon, Field and Grasslands, a New Guide. I'm Taylor Thomas, and I'll be your moderator today. Joining us today are two experts, Jamie Pierce, who is Vice President of Professional Services and Commercial Development at LI-COR. Jamie brings expertise in sensors and instrumentation and helping users apply these tools for high quality data in multiple industries and use cases. And Jamie leads our professional services team at LI-COR. Uh, we also have George Burba, Dr. George Burba, who is Science and Strategy Fellow at LI-COR. Uh, Dr. Burba is a leading voice in ecosystem flux science with decades of experience in carbon measurement and environmental monitoring. Dr. Burba has played a pivotal role in helping to translate the tools used within the scientific community into broader adoption and practice across multiple industries. The topic today is uh, harvesting carbon and really understanding that carbon plays a vital role in things like crop yield, soil health, sustainable land management. Accurately measuring carbon exchange is essential for evaluating management practices, and that's where these direct measurements really come into play. And this new guide focuses on how to apply these techniques effectively in field and grassland settings. So we're really excited to explore how this guide can support more accurate, reliable, and cost-effective carbon management solutions. Before we get started, just a couple of points. Please post your questions to the Q&A section of the webinar. We will address these questions directly, and we'll also have an opportunity to address questions as part of a group at the end of the presentation. We are also recording this webinar, so if you have colleagues who are not able to join, we will be sharing the recording and invite you to share this among your colleagues so that they can get the information as well. Finally, if you plan to attend EGU or AOGS or AsiaFlux or AGU, we can discuss any of these topics in person, and our presenter today, Dr. George Burbo, will be present at I think most of these conferences, so we'll have an opportunity to discuss this in person. So with that, I'll hand things over to Dr. George Burba. Thank you.
Thank you very much, Taylor. Just checking, like everybody can hear me, right?
Yes.
Yes, okay, all right. So I'll start on the presentation. Thank you everybody for coming. It's very nice to virtually meet everyone. And today is fairly simple presentation. It's about a new guide, which called Harvesting Carbon. It's one of the three guides in this three guide series. And this one specifically dedicated to the short canopies of fields and grasslands. First, I'd like to introduce LI-COR as a company to people who not familiar with LI-COR. For over 50 years, we innovate by turning complex methods, systems, and instruments into sophisticated yet simple to use solutions. And we focus on natural resource management, agricultural practices optimization, and a very wide range of environmental research. And here, if you could see my mouse on the left, this is how this type of measurements, this flux measurements, were done in early 2000s. And this is not stock photos. These are actual photos from measurement sites and the data processing center. So in the middle, this is one of the more compact LI-COR solutions, much more sophisticated and faster and low power, which we did in 2010s. And it already had the cloud type of platform with it called Flux Suite. And now very recently, just a few months ago, we developed even smaller, cheaper, much more low power solutions, which are very good for practical applications. And we have also improved our cloud, and we are on different type of cloud now. In terms of LI-COR scientific impact, many of you may be familiar with the impact factor and journal citation indices and so on. And here is the just curious table of how often our instruments are cited. So if our instruments were authors, the LI-COR environmental would be sitting just below Brown University and above Boston University in terms of citations. So we are very fortunate and proud to have such a strong scientific impact on environmental community. So this presentation, first we'll briefly talk about current state of carbon markets. Then we'll discuss the difference between direct measurements and not direct measurements. Then dive into the most popular and widespread direct measurement of the emissions and sequestrations EDICA variance. Then discuss a little bit what the guide's actually for, and I'll show you several things on the basic knowledge where you can go and check if you want to go deeper. So let's look at state of carbon markets. If we had to put it in one sentence, they significantly undervalued because of uncertainties. And they currently evolve from voluntary goodwill and advertising paradigm, when people say like, oh, I want to offset my fuel, so I will buy somebody else's plot of land, into commodity-like trading paradigm. This is when if you sell something, you put it on the scale and you measure exactly what you're selling, and that's how you determine the price. The current system of MRV, it's measurements, monitoring, reporting, and verification. Sometimes people call it MRV, atmospheric MRV, AMRV, digital MRV, TMRV, and so on. It also evolves from approximations to actual measurements. And the currently used approximations, like emission factors, sampling of one partial carbon pool, for example, biomass without soil or roots, or soil without roots or biomass, they still remain useful for long-term benchmarking, particularly for permanency. But they are insufficient for active carbon management or for monitoring of total carbon pool. Well, because first, they approximate things. They don't actually count how many molecules of CO2 were removed from the air. They also focus on partial pools. So it's either soil or biomass. And because of their error bar and time it takes to build the carbon, they only go like every few years. So they're not frequent in time and space. And if they were to be applied correctly, they would be extremely expensive. And we're talking about sampling soil down to 1 meter at least in multiple hundreds locations in every field, and then sampling biomass with roots. And that becomes very, very expensive if we wanted to achieve the same accuracy as some of the methods we talked about today. So because of this, because of what's happening with methodology, this could be reason why carbon market remains generally ineffective for reducing GHG. So the CO2 was 360, then 380, then 400, then 420, and no matter how we're trying to trade it right now, it's not going down. So maybe there is a better way to start trading it and to make sure it's actually start going down. And by the way, everything I'm talking about here, I'm referring to CO2 because guides are about CO2. But water and other GHGs are very, very similar in terms of measurements. And water markets definitely in much better shape, but most of water markets still use indirect measurements of water loss. And most of the methods in water markets don't actually measure water. So now let's look at the quote unquote new approaches. They are new to these markets. They're not new to the science or environmental science. So we have direct and continuous methods to measure carbon, GHG, evapotranspiration, water loss, heat emission from areas. And these methods measure, for example, CO2 removal from the air every 30 to 60 minutes. And you have a data point and you know over that time, and they measure continuously. They existed in academia for over 50 years. But now they can be applied to practical needs because of technology improvement. And these methods can complement and in some cases possibly replace the existing approximations. And they are in general called power flux methods. And most direct of them are turbulence-based methods. There is a large group of methods with different flavors where you're actually measuring how many molecules coming up or down, and how many of them are fixed and how many of them are leaving into the air, and you look at the net exchange. And this is as direct as we can get. Then another group, it's methods, they kind of a little bit older, but they still in use and they cheaper. This is gradient-based methods. That's where you measure gradient of, let's say, CO2, and you determine the exchange coefficients, resistances, and then you try to compute fluxes. They're not exactly direct because all of these exchange coefficients, resistances, diffusivities, they're all different, and it makes it, you have to make assumptions on those. And then, of course, we have models with field verification. And there is a group of models, they're very approximate by themselves, but if you feed direct method into the model is becoming better. So perhaps the best approach, you use direct method for the particular spot on the ground, and you use model to scale it up to larger areas. Let's look close into direct measurements now. So we're all familiar with weather stations. They like at airports, at schoolyards, and so on, so everywhere. So, and combined with remote sensing and weather modeling, this weather station provide us with weather inventory and forecasting. That's what we're actually seeing on our phones, for example. This is the remote sensing based weather model continuously tuned by actual measurements by weather stations. And they used for daily decision making, charting courses of cargo ships, rerouting airplanes around turbulences and trains, and so on and so forth. So this is pretty familiar concept. The lesser known is similarly looking stations, but they are flux stations. Those, in addition to weather, directly measure emissions and uptakes of gases, water vapor, and heat. And they were mostly or overwhelmingly in the academic space. And now they're just moving into the general public space. But they've been used since 1980s in thousands of locations globally. And for particularly turbulence research, ecological research, climate research, and they provided precise and continuous hourly measurements of GHG, sequestration emission rates, evaporative water losses, and heat emission from the areas into the air, and vice versa. So why they were sitting there for so long, like for 50 years? Well, they were complex and expensive. When I started in 1993, we had to have the large trailer and about 6 people to run just one of them. So this is a big enterprise. But in the last 5 to 10 years, technology changed very significantly. We have designed things with nearly full automation. Resolution is now remarkable. Power consumption is remarkably low. And there is no reason why this technology cannot be used outside academic research for decision-making and resource management based on direct, accurate measurements. And the immediate benefits outside of academia would be greenhouse gas monitoring, carbon sequestration, trading and offsets, leak detection, landfill monitoring, CCUS, irrigation scheduling, water management, everywhere where we have to use indices, emission factors, and other proxies, we can now use flux stations. And among these flux stations, the eddy covariance method is by far the most established, probably 98, 99% of all of them as eddy covariance. So it's been worked through, the methodology has been worked through by micrometeorologists since 1980s. The method is matured. The protocols are established, workflow is established, data processing and data structure established, because there are national and international networks, flux networks, which were getting particularly active from early 2000s to standardize everything. And also full automation helps people who don't need to understand every little detail of how station works. So systems available with nearly full automation since mid-2010s. And overall, this provides exceptional way to measure greenhouse gas emissions or sequestration. So this is the map of past and previous locations of all eddy covariance stations. So some regions are covered very well, and it's not only this kind of coverage is important where you actually measure it on the ground. Of course, that's important. It's also important that you have data sets in so many places to develop and tune the models so you can scale the stations. And of course, you also can see which regions are underrepresented, and maybe you can put additional stations in there. This way, the modeling and scaling will work much better. Let's now look how eddy covariance method works. So standard setup is pretty simple. You have sonic anemometer, which measures vertical wind speed. And you have a gas analyzer, which measures how many molecules of gas or water vapor in each up and down motion. And these motions, up and down motions, they happen very, very quick. So it's going to be 3 molecules up, 2 down, 5 molecules up, 1 down. And over 30 minutes or over 60 minutes, you know exactly how much went up or how much went down. And on your right, you see the latest implementation. This is fully automated combined sensor, where the vertical speed is measured here. If you can see my mouse on the left between these two C-clamp transducers, and just next to them, we have gas analyzer measuring gas and water. And a lot of the stations typically have additional, we call it biomed parameters to help interpret the data or gap field data. It's typical key drivers like solar radiation, air temperature, soil moisture, and so on. So mathematically, the method works by looking at turbulence. Airflow could be imagined as horizontal flow of numerous rotating eddies. Eddies are little tiny vortices, little tiny circular motions in the air. When wind comes and wind hits the obstacle, it starts breaking into these turbulent structures. Also, if it's very smooth, let's say like a desert, but it's hot, the hot air will rise up, but wind is trying to go horizontally, and it will tumble over this rising temperature structures, like rising warm air parcels. So you have shear turbulence caused by objects and buoyancy turbulence caused by difference in density. In any case, during daytime particularly, most of the transport of everything from the air into the ecosystem and back, or field and back, is done by turbulence. And that's what we are measuring with eddy covariance. A lot of people who are new to this, they ask a very good question. They say, how is that you, if something comes from very, very far away, like for example, gas concentration, it doesn't affect your measurements? Well, because we only see, the eddy covariance sees the covariance between vertical wind and between density. And that covariance is formed in the upwind spot from the station called footprint, which is about 100 times the station height here. So if 3 molecules come from somewhere else, and this area in the middle doesn't add anything to that mean flow, the eddy covariance station here on the right will measure 3 up, 3 down, 2 up, 2 down, 3 up, 3 down, 4 up, 4 down. So the flux from that area in the middle is 0. But as soon as the same 3 molecules comes from somewhere, but that area, so now we're looking at the bottom plot, the area adds, let's say, CO2 into that mean flow. Now we have a gradient, and that gradient must go somewhere. And the mechanism for the transport is turbulence. So what we'll see at the station, each upward motion will be biased slightly than downward motion from eddy covariance. So it's going to be 5 up, 3 down, 4 up, 1 down. And that's the actual direct physical flux. And it could go up, upward, or it could go downward, where we would see like sequestration happening in real time. So the eddy covariance is a cutting-edge technique to measure fluxes, emissions, and exchange rates of CO2, methane, and all water, heat, and actually turbulence itself. It's nearly direct way to measure transport. It represents exchange of an area, roughly 100 times the tower height. And it represents the entire ecosystem of field scale exchange, not just partial carbon pool in case of carbon. And the eddy covariance throughout this history was so methodologically developed that it's very flexible to set up to fit various range of goals. You almost always have somebody who did similar work already for years and years, so you can easily consult those people. And here I'll give you, this is probably most important part about this presentation. That shows you the difference between active monitoring and measurement and monitoring of carbon versus what's done now. So in the top left plot, you can see the actual case. There are two stations, two eddy covariance stations at two very similar pastures. And here they were run in the same exact carbon management manner. And here the fertilizer was added, the red dot. And you can see immediately that effect of the fertilizer on the pasture where fertilizer was added. So by the end, it was nearly twice as much in sequestration by adding that fertilizer. So you can evaluate your carbon management. You can see that effect, and you can price that effect in relation to the fertilizer application price right away using direct method, and you can see results immediately. Present methods will only give you results for partial carbon pool every 5 years. So you wouldn't know if this worked here. And if in 1 year you have applied fertilizer and the next year you had a drought, you think that there was no effect of the fertilizer. So you wouldn't know how it was managed. And then you're getting 0 carbon sequestration dollars. However, if you measure it continuously, you should get your credit for the first year and your insurance for the lost credit for the second year. And that's one of the big advantages of continuous direct monitoring. And the next plot at the bottom right, just to show that not all fields are created equal. They have very different carbon emission and sequestration patterns. So this is another year. The top plot was 2 years. This is another, here's 1 year, and you can see alfalfa versus rice. So however you manage, wherever you're looking for the drought probability and additional irrigation application, and things like this to keep your canopy green and growing, this type of data become very important. Now back to the guides. First, I'd like to thank lots and lots of people and organizations, because these guides essentially condensed, very, very condensed and simplified version of the knowledge by all of these organizations listed in the green. And all of these people and organizations listed in these pictures below. And I'd like to thank everybody who helped to design the guide and review the guide from different places globally, including LI-COR, but also like from France and US and so on in blue. And I'd like to also thank people in red who helped design the actual guide, physically the guide and illustration to this. Thank you so much. So as I mentioned, it's the first one in the series of 3, and it's based on the multiple scientific academic books on eddy covariance. And the guide is not designed for scientists. The guide is designed for the environmental entrepreneurs and investors and various upcoming carbon registries and carbon sequestration companies to develop projects seeking to establish and verify carbon sequestration rates, generate related credits based on the direct quantification of fluxes in and out of the air. The idea is that this guide can serve as a skeleton for writing individual carbon protocols. So if somebody has specific solution, specific fertilizer, specific cover crop, and so on, they can develop that solution and then build up very quickly on the guide, like copy paste it into the guide or copy paste parts of the guide into their solution and create their own protocol. The guide is also done in a very different way. I try to write it that steps are certifiable. And what I mean by this is, like, did you do or did not you do step 1.7? Yes or no? If you did, as described, the 1.7 is certified. If you didn't, it cannot be certified. So it's very prescriptive. It's prescriptive on purpose, so anybody can use it to establish reliable protocols. And as a result, we hope to move carbon market into reliable standardized MMRV platform for continuous direct monitoring of all carbon pools, particularly for two types of measurements. The short-term measurements when you develop recipe, when you compare multiple treatments and you say like, oh, I compare this new carbon management with that carbon management with the baseline, and you develop it like maybe you run it for 6 months, maybe you run it for 12 months, but you see immediately that between your different treatments, one is much better in sequestering carbon. So that's one. And another one is long-term continuous monitoring of this type of solutions, or forests, for example, and so on, where you put the station there, it's always there, and it just gives you the direct carbon sequestration or carbon losses throughout the year. So you can model it, forecast it, and manage it actively. So the guide outlines minimal set of essential steps for planning, installation, data collection, processing, quality control, and reporting. And it's minimal. You cannot not do any of them. You cannot miss any of the steps. There are other steps you can add, but you cannot miss any of those. And the guide is focused primarily on the LI-COR's latest solution, the carbon node. And carbon node is this type of station with low power, reduced cost, flux station measuring CO2 and water vapor, combined with LI-COR Cloud, where the data are cleaned and gap filled and so on nearly automatically. And because it was much easier to write very specific guide, very prescriptive steps to have a single system in mind. However, it will work, the guide will work correctly with any station which is designed correctly without cutting corners. I also put there steps that you cannot cut corners. And I don't want to go into details of cutting corners, but there is a lot of cutting corners been lately. If we keep doing it with cut corners, I don't think we're going to move the carbon market. The guide also refers to LI-COR professional services. And again, this is something a lot of people in the institution probably will find much easier and cheaper if LI-COR provides these services to them. So we will come, we'll install everything, we run it for you, and we give you the final numbers. Or any part of this process we can fulfill. However, if people want to do it themselves, if they were set up and they have department or they have experts to do it, again, guide will work without LI-COR professional services. And here is a couple examples of this. One is the same plot. So let's imagine we're trying to develop short-term new treatment and see the short-term effects of it. For example, it could be fertilizer or biochar. And we have one field, there's a baseline, business as usual measurements, we're not adding anything to it, and another field is new treatment. And the company or the entrepreneur who writes, who develops this recipe, they write their own steps. How much biochar you apply, when, where, too much, to what depth, and so on and so forth. So they start on their own protocol already. And they make sure that each of their steps is certifiable. So it's written in a way it's yes or no. And then they can add their steps into existing harvesting carbon guide. So there would be a recipe how you manage the carbon, then how you measure the carbon. And then it could be after you measure the carbon, how you adjust. Or you can do it the other way around. You can write your own protocol for treatment and make sure that, again, it's certifiable. And then you copy paste parts of harvesting carbon guide into your protocol. So in either case, you end up with in much shorter time with certifiable protocol created for your particular carbon solution or carbon monitoring need. And example 2 is that long-term observation. Let's say it's land remediation. And this plot shows you the actual carbon accumulated over many years, sequestered by Harvard forest. You can see that during summer accumulation increases, and during winter it loses a little bit of carbon, then it gains a little bit more every summer, and so on and so forth. And it has a pretty large net gain over many years. So let's say you're planting the forest to remediate your land, and then you monitor it in perpetuity to take advantage of all the carbon being sequestered in that forest, in your remediated land. And similar, like with the first example, you can either add your steps, how you plant, what species you plant, at what density you plant, how you irrigate, so on. You can add all of your steps to the carbon guide, or you can add carbon guide into your own space. So in either case, certifiable protocol is now created for long-term, ongoing, direct, continuous monitoring of carbon sequestered. So there are been some developments this year in general on this eddy covariance-based protocols for carbon sequestration. The first protocol developed by Hyphen Global with social carbon registry has been accepted. So we have official accepted eddy covariance-based protocol for carbon sequestration. And the second protocol, which was actually filed earlier, but the process takes longer, was by Carbon Space with International Carbon Registry, and it's currently under review. And we plan several more protocols, start working on several more protocols based on the guides with several different organizations. And we're going to add high resolution flux mapping, multiple distributed stations approach, interpolation, extrapolation with remote sensing and AI, and adding permanency scenarios and verifications. So we're turning this carbon guide, which is written for one or two stations in very, very specific prescriptive manner, into the bigger eddy covariance-based carbon protocol. And in another interesting development, that major registries, which were quite resistant to the direct measurements, they recently start hiring eddy covariance scientists. So that tells you something. So basic knowledge. So if you're interested to learn more how the method works, you can go to different things. But first, let's tell about other couple harvesting carbon books. So the next one coming out will be on the tall canopies, forest, orchards, and wooded wetlands. And then the third one would be on lakes, ponds, and regular wetlands, because there are some specifics how you deal with tall trees, and there are some specifics how you deal with water bodies. So in order to have it prescriptive and certifiable, you have to have them as a separate guides. But the methodology itself and how it works exactly is described in this 2022 book, which you can download for free. And this is 700 pages, so be careful with this one. But it tells you everything you need to know about the methodology behind the guides. And thank you very much. And we are open for questions now.
Excellent. Yes, thank you very much, George, for that great presentation. We do have a number of questions here, and if others have questions, please go ahead and post them to the Q&A section. But I can make maybe this first question for you, George. Eddy covariance is known for its accuracy, but also for being technically complex. What are the biggest challenges users face when applying this method in the field, and how does the new guide help address these challenges?
So the biggest challenge in eddy covariance, like before, never changes, is that people do not plan ahead. They go and install, and that's almost always wrong. So like before you go and install, you need to have a very detailed plan, like what you're trying to achieve, what variables you need to achieve this, And that informs you where to put it and how to put it and what equipment to use. And it's described to the yes or no degree in the guide, and it's described very detailed in the book, in the 2022 book. So that's the biggest challenge, is lack of planning. And second challenge is more methodological. You have to maintain the station. If you don't maintain the station, if you have small gaps, you can fill them easily. If person forgot about station for 4 months, that's going to destroy the accuracy of the long-term sequestration measurement. So the stations must be maintained. So somebody has to watch them and maintain them same exact way like with weather stations. The paradigm on the technological maintenance is no different from weather stations. Everything weather services do needs to be done here.
Excellent. Yeah, thank you for that, George. Another question came in asking about the guide. It emphasizes tailoring measurements to site-specific conditions. What variables like vegetation, topography, or climate most affect how these systems are deployed and maybe interpreted?
Yes. So the guide, first of all, topography. The eddy covariance can work in complex topography, but that requires different calculations which will not be automated. So like when you the guide describes when you select the site, what topography is acceptable and what topography is not acceptable. It gives you the pictures. Like, does your area look more like this versus more like this versus more like this? If it's like this, you can use it. If not, do not use that plot. Find another plot with flatter topography, for example. So that's topography is one thing, and the canopy height you'll need to know, because and the guide describes exactly, depending on the canopy height, what your tower height should be.
Mhm. Excellent. Yep. Thank you for that, George. Maybe next one here for Jamie on the line. Um, mentioned LI-COR professional services as a way to stand up a monitoring program. How would someone get started with a monitoring program with LI-COR professional services?
Yeah, sure. Taylor, it dovetails in with what George described. So, especially the site selection, where the instrument should be placed. Um, LI-COR can be contracted to assist with that with our field scientists. So you would think of it as contracting with our field scientists on a consulting basis, and it doesn't take that long. Essentially, we'd be looking at Google Earth KMZ files, looking at the location, working with the end customer for the requirements and the wind roses of the area. Once that's defined, we can make our recommendations of what instruments are needed, up to and including the actual installation and even assisting with the data analysis and final data proposal at the end. So it can provide a full turnkey services through professional services.
Great. Yeah, thank you, Jamie. Um, maybe going back to George here, is a question about the protocols themselves. What does the impact of the presence of a protocol have globally? Do different protocols only apply to specific regions or to specific crops? Are there any universal carbon protocols?
Uh, the eddy covariance is the universal method because it measures same exact way over field, over city, over wetland, over ocean, doesn't matter. And that's the beauty of it because it's apples to apples. However, setting up the station is very different over the water, over tall canopy, or short canopy. And three guides will address that setting up, how you set it up, that it remains apples to apples. Because, for example, I'll give you an example. If you have short canopy and you set up eddy covariance 2 meters above it, and you see 200 meters upwind, if you simply set up your station 2 meters above 40-meter forest, oh, it's going to be bad. In order to compare that short field with that tall canopy, you have to install your station much higher. And protocol tells you, there is a table in the protocol saying, okay, this is my canopy height. And so this is the range where it needs to install my stations, my instruments. And this is the ideal part in that range. So yes, so the methodology is universal, but setup isn't. Yeah.
Great. Thank you for that. Another question. Can you share briefly what the protocols are supplementing EC measurements with examples, chambers, ancillary data, biomet info?
Yes. So if you want to explain why things change and forecast the future change in things, you have to have supplementary things. Particularly, you have to have biomet, and in Carbon Node, we have all of this. So you have to have soil measurements and soil temperature, incoming radiation or incoming PAR, because they drive the growth and they drive the temperature, and all the weather parameters. Because the moment you are in either trying to understand the relationship or forecast it, you're going to be in some type of modeling environment. Simple number of carbon sequestration is not enough to model carbon sequestration. You need to know what drives it. So, and for chambers, this is sort of unique because there are processes which are driven, for example, primarily by either soil or water. Like, for example, there is ebullition of methane in the water bodies. And if you were to develop some solution about this, perhaps you also want to have chambers on the water, for example, to see if your method works at the place where you design it. You still need to see a covariance that it works over the whole territory. But in your development of recipe, you might need this like individual, it's like a microscope saying like, oh, but what happens with my ebullition, my bubbles in that water? Should I have water deeper or vice versa or shallower and stuff like this? Yeah. Or microbiome comes to mind, fungi. There are processes which are specific to the soil, and chambers can be very helpful there. It's not covered in the guide, but yes, this would be supplementary protocols.
Great. Yeah, thank you for that. And we keep having questions come in. Thank you for the questions, everyone. I'll keep going here. We have another question. What do you think are the incentives for companies currently managing carbon sequestration projects, i.e. reforestations, to opt for this method and not stick to a traditionally employed and nowadays considered maybe cheaper approach?
Well, they're cheaper for a reason. Then that's what they do. When they say like, we're going to measure soil core, because soil core is most accurate methodology, because we can resolve, we're only going to measure permanent carbon sequestered in the soil core. And we can do it every 5 years. So we see from 5 years to 5 years what we have in soil core. And then they cite the papers which do it. It's all correct. There is nothing wrong with it, with the caveat. In order for the person to actually measure the carbon sequestration in that field with 5% error bar, they cannot measure down to 30 centimeters. They need to measure to 1 meter, sometimes deeper. They also cannot measure it in 5 places in the field. They need to measure it as 500 places in the field or maybe more. Only then they will achieve what they've cited. So they cite very expensive, unique study, and then they go and they do 5 samples in the field down to 30 centimeters. So there is a complete disconnect. It's because it's excruciatingly expensive to do it the right way. And you're still missing all the biomass. You still cannot do staining biomass or roots. And you're still missing the active carbon management, because if you change something, you don't know if that worked or not. And if it worked, how well it worked. You're going to have to wait another 5 years. So these are the advantages. I don't want to like bash too much on existing stuff. They did what they had best. There were no better tools. They did their best. Okay, now we have something better. For permanency, I still think from time to time it should be like soil carbon core and biomass should be done in the small subset to the proper depth with proper density. Then it will give you the idea of permanency. But for active management and for active market selling and buying and so on, I think the direct observations are better.
Great. Yeah. Thank you, George. We have another question here for you, George. What about the so-called lateral fluxes, i.e. the carbon that is taken out of the field through harvest? by just knowing the net ecosystem exchange, it doesn't give you a number for the actual harvest.
It's the same as with soil core or with any, the lateral fluxes apply the same exact way to existing methods. If you're removing something, you have to decide, did you just incinerate it into the air, or is it still sequestered, or part of it is sequestered? Like if you remove trees and you sell boards, they're probably going to be sequestered for 200 years. Well, if you remove grass and feed it to the cows, well, they're probably not going to be sequestered. And so anything, I propose that anything outside of the field is treated in a separate treatment. This is not in the guides, but this is just different approach. Because right now, like if farmer puts cover crop on, for some reason, we're also asking farmer to see like how much energy grain dryer using and how much carbon footprint is in the grain dryer. This is not farmer's problem. Farmer sequestered X amount in this pixel. Then somebody transported it to the grain dryer. So this person who is transporting it, they cannot sequester anything because they're transportation, but they can improve from the base. They can use different fuel, or they can use electric trucks. Similar with the grain dryer, they don't have to use, they again have no hope of sequestering anything, but they can improve from the base. They can use hydro energy, or they can use solar energy and improve from the base. And then the parties responsible should be responsible for their stuff. Like the person who grown something green sequestered carbon. And that's why current market is all intertwined, and it's not commodity market. It's a scientific, philosophical thing which really doesn't work yet because the carbon doesn't go down. So perhaps my hope is we put it on this direct platform. So like pharma sequestered X. This biomass was removed. The person who removed it responsible now for that biomass. That person sold it to somewhere. These people now responsible for that biomass, and they all can, in their particular domains, do improvement from the base. And then we can figure out permanence depending on what's being sold. Is it wood versus grain versus grass, and so on.
Excellent. Yep. Thank you very much. Couple more questions here. Thank you again for all the questions. This one is a little bit more on the practical side of things, and so this might be for both you, George, and you, Jamie. How would a project be defined and executed? Do you need to have a baseline deployment for comparing fluxes against some management treatment?
Yeah, I think you can chime in, George, but the ideal is to have a baseline. So you're obviously want to have a control area for whatever you're trying to measure in a similar size. And from a strict evaluation, if you weren't going to use a control area, it takes almost a full year to benchmark an area to then put in your instrumentation. So obviously from an efficiency standpoint, it's better to have a control area that doesn't have the treatment that you might be doing or the ecosystem changes that you're trying to measure to get the carbon credits that you're trying to establish for your primary area. Yeah, George, does that align with your expectations?
Yes, it's like it's cleanest, most defensible if you have baseline. It could be neighboring field, or you could have like time before. Time before is less defensible because people say like weather changed, which is kind of true. But if you have one reference and one treatment, okay, that's very defensible. And you keep them, you don't even have to keep them 1 year without treatment. You can keep them for a few months just to show, okay, it's the same soil, it's the same grass, and we see the same fluxes. Okay, so we're fairly confident they're going to function in the same way. And now we're changing one of them with a new treatment. That's probably most defensible approach. Yeah.
Excellent. Excellent. We have one final question here. Some registries are currently asking for different pools of carbon to be declared. Eddy covariance may be blind to this kind of partitioning regarding autotrophic and heterotrophic or non-respiratory carbon losses. How is this addressed in the carbon crediting scheme?
Well, they need to stop asking for pools, right? Because that's what they can do. They're asking not because there is some mysterious knowledge in it, because they're trying to do pool by pool. and they never can do total. So yeah, I don't know. That in my opinion needs to be changed.
Mhm.